Hi guys, we're going to talk about bond order and bond length. So let's start with bond order. So bond order kind of tells you what kind of bonds are the average of all the bonds in your molecule. For example, if the bond order is 1, that means that the average of the bonds in the whole molecule are single bonds. If the bond order is 2, that means that the average is double bonds. If it's 3, then that means the average is triple bonds, and so on. So to calculate bond order, which we're going to call BO for short, you take the number of the bonds to the central atom over the number of atoms bonded to that central atom. So to do that, we're going to start by drawing our Lewis dot structures. So CH2 Cl2 looks like this. And we'll do our lone pairs. There we go. HCCH looks like this with a triple bond in the middle. And then SO3 has resonance, so we have actually 3 resonance structures. So I'm going to draw 3 of those. That's an O there. And so in my 3 resonance structures, I could have my double bond here, here, or there. And then you put in all your lone pairs. So for all the ones that the oxygen is double bonded, you need 2 lone pairs. And then for the oxygens that are singly bonded, you need 3 lone pairs on each one of them. Lots of lone pairs. And our last oxygen here. All right, there we go. So now, to calculate bond order, go ahead and change the color here. So for this one, we would say the bond order is equal to, you take the number of bonds to the central atom. So our central atom is this carbon right here. And so there are 4 bonds around it. And that's divided by the number of atoms bonded to that central atom. So this carbon is bonded to 4 different atoms. And so 4 over 4 gives you 1, so the bond order is 1, which means that the average is all single bonds, which in this case makes sense because they all are single bonds. So let's look at this one if we wanted to find the bond order. Now here you can pick either one of those carbons as your central atom. So let's pick this one as our central atom. So you take the number of bonds to the central atom. So this carbon has 1, 2, 3, 4 bonds. Oops, sorry about that. And you divide that by the number of atoms that are bonded to that central atom. So this carbon is bonded to 2 other atoms. And so 4 over 2, this gives you 2. So the bond order for this molecule is 2, which tells you that the average for this carbon is a double bond, which makes sense because you have a single bond and a triple bond, so the average between them would be a double bond. Now, bond order can be a fraction. It does not have to be a whole number. So if you look at this here, it doesn't matter which one you do it for. They're all equivalent. But in any of them, the sulfur is your central atom. And so around that central atom, we have 1, 2, 3, 4 bonds. And then divided by, we have 3 atoms bonded to that sulfur. So 4 over 3 is our bond order, which is a fraction, and that's fine, or 1 1/3. So what that means is that the average is a bond and a third, which in this case, remember that all of these are equivalent. It's not a double and 2 single bonds. All of them are actually a bond and a third. All right, so that's bond order. Now let's take a look at bond length. So bond length is what it sounds like it is. It's the length of a bond. So sometimes we call that the internuclear distance. Internuclear, let's see, distance. And it's also sometimes thought of as the distance between the nuclei of 2 bonded atoms. Distance between the nuclei of two bonded atoms. Which means internuclear distance, because inter means between, obviously nuclear means nuclei, so it's the distance between the two nuclei. So bond length depends on two things. It depends on the radius of the atoms that are bonded together. Obviously, if you have two really big atoms bonded together, then the distance between their nuclei is going to be really big. If you have very small radii of the two atoms that are bonded, then the internuclear distance, or the distance between the two nuclei, would be small. So here we're looking at all carbons, so that part is the same, and then that carbon is bonded to either a nitrogen, a carbon, or a phosphorus. And so the bond length in this case is going to depend on the radius of that nitrogen or carbon or phosphorus. And so if you look at the periodic table and the trends on the periodic table, remember, it looks like a one-armed snowman, right? So the radius increases as you go down the periodic table, decreases as you go across. So between nitrogen, carbon, and phosphorus, nitrogen is the smallest in radius, and so this is going to be the shortest bond. Followed by carbon, and then phosphorus is the largest atom out of those three, and so this is going to be the longest bond, or the longest bond length. Okay, so obviously the number one thing would be the radius of the atoms of the bond atoms that are bonded. The second thing that affects it is the bond order. So if you look at this example here, we have all of them are carbon and oxygen bonded together. So obviously the radius of carbon and oxygen are going to be the same here, but the bond order does matter. And it turns out that the higher the bond order, the shorter the bond. Let's write that down. The higher the bond order, the shorter the bond. So if you think about it, if you guys were in school right now, what I would, the way that I would demonstrate this is I would have two students, and they would extend their arm like this. Stay as far away from each other as possible, but extend their arms so that their fingertips touch. And that would be like a single bond. Okay, so you're pretty far away from each other. Now, to make it into a double bond, I would tell you that you need both of your hands extended towards each other as far as you can from each other, and both of your hands need to touch. And so you're going to get a little bit closer to each other. With a triple bond, you'd have your two hands extended and touching, and then also your knees, and so then you'd get even closer. So the more bonds that you have, the higher your bond order, the shorter your bond gets. Your nuclei get closer to each other. And so out of the single bond, double bond, or triple bond, carbon, oxygen, this would be the shortest. And then this would be number 2, and this would be the longest bond. Another thing that we need to know about bond length is that the shorter the bond, the stronger it is. Go ahead and write that in different color. The shorter the bond, the stronger it is, and the more energy required to break it. So remember that bonds, when we break them, that is endothermic. You have to put in energy to break a bond. When you form them, it's exothermic. So imagine that this pencil was my bond. It's kind of long, And so let's say I want to break this pencil. And so I have to put in energy in order to break it, and it breaks pretty easily, right? It's kind of long, breaks easily. Now let's take a shorter pencil, or even, half of the pencil that I broke, and then you try to break that, and it is much more difficult to break, right? I can't even break that. It's pretty tough. And so the shorter the bond is, the harder it is to break. So if you are comparing between these three bonds, you'd say this one is the hardest to break. It would take the most amount of energy to break versus this one versus that one.